Lecture 85 is now going to describe the thermal expansion tensor since we set up the background in lecture 84 for thermal expansion, just showing that it's the imperfection of the harmonic potential as you continue to increase energy that leads to a thermal expansion away from the mean bonding distance. So given that, we can do a simple one-dimensional demonstration of that. Imagine we have our bar L at some T1, we go to T2. The bar is now longer. So it's gone to L plus delta L, pretty straightforward. As we have shown in the last lecture, that there's, with an asymmetric well, with high enough temperature, you end up seeing that delta L is proportional to delta T because X and U are proportional. And so you end up with alpha, the thermal expansion, is being defined as this delta L over delta T. It's linear. The larger the delta T, the larger the delta L, normalized to the original length. And of course that is very much like a strain. And so we can then model it that way. You would say that I end up with strain, from this delta L. The only difference is instead of pulling on it, right? Normally I was, using sigma, but I'm not going to have that this time. So I'm going to get a strain, but the driving force is actually temperature, which is a scalar and not a tensor vector. So that is interesting. And so that thermal expansion becomes a little bit different that way because it's not driven by a vector. Another odd example of how tensors are involved, but not necessarily only interacting with vectors. Now what I've drawn here is that the off-diagonal components have to be equal. And this is because we essentially have a scalar, so delta T just goes and it changes this thing, and our well is assumed to be in all directions, in the different directions. Doesn't matter whether it's X, Y, or Z. The way we've kind of set this up, there's no way to have an imbalance across this with a scalar times something that's linear in delta T, delta L. And so for that reason, these off-diagonal elements are equal to each other, and therefore the strain that's induced from this, so this is a scalar, this is our thermal expansion tensor, and this is the strain tensor. And there you have the thermal expansion. A very important aspect of materials. A quick example is that all these expansion, because the bonding curves are, not different in terms of orders of magnitude, so the values are all very similar. If I have a substrate that's very thick, let's call it silicon. and I deposit a useful material that has different properties, like say gallium arsenide, which emits and detects light better. And this is very thin. What happens is that the thermal expansion of the substrate is going to control the cooling down. So if I deposit this gallium arsenide, let's call it gallium arsenide, and I deposit it at say 700 degrees, and I'm cooling down to 700 degrees C, right? And I'm cooling down to room temperature, right? I have hundreds of degrees of temperature cooling. And if this, let's imagine, as it turns out, they are substantially relaxed at the growth temperature, right? So the gallium arsenide is perfectly happy the way it's accommodated the lattice mismatch. It turns out these have lattice mismatch, which is another kind of stress. But let's imagine all that stress has gone away because I'm at high temperature that's been annealed out, and so this film on this substrate is perfectly compatible. It's relaxed. I've introduced defects, and so at the growth temperature, everything's in its like base state. Now, when I cool, you have silicon that cools at, let's say, about 2 times 10 to minus 6. In 2 times minus 6 in its inverse temperature, because over here, whatever I put in here, when I multiply times temperature, it cancels the temperature apart in here and then produces the strain, right? And so you can see here that now gallium arsenide is about 4 approximately. I mean, these are just rough numbers. 4 times 10 to the minus 6 inverse Kelvin. So you can already see here that when I have hundreds of degrees temperature change, right, I'm going to end up with, say, 10 to the minus 4 strain. And 10 to the minus 4, 10 to the minus 3 strain. Well, actually, to see that, let me finish what goes on here. So as I cool down, what happens is the silicon dominates the lattice constant, right? So let's imagine that I have, some relative lattice they're both happy with, and it's, A. When it cools down, this thing's trying to contract to be, A, times 1 plus the epsilon ij that I mentioned, which is, essentially A times 1 plus alpha ij delta t. So you can see where this is going. I am going to produce a stress just from the fact that these two are cooling at different rates, but they're linked. They're linked so that they're not allowed, this top film, if this is much, much thicker. So the substrate thickness, let's call it H sub, is much, much greater than the film thickness. Then essentially the film is forced to go at the rate of the substrate. You can see here this has a higher thermal expansion. So it wants to shrink faster, but it can't. So you can tell what's going to happen is, since the silicon controls everything, the gallium arsenide is going to become under tension. That's a little confusing because, wait a minute, I got to think about this, right? But look at it's got a greater alpha. So if it's got a greater alpha, its lattice is going to try to shrink faster for a given change in temperature, right? So as it tries to shrink, it can't shrink as fast as it wants because silicon has a smaller alpha. And so as it shrinks, it's going to want to be actually closer together. The atoms are going to want to be closer together, but they're forced to be further apart. Atoms being forced to be further apart means that they're under tension. In fact, it's biaxial tension, right? So you actually induce a stress from this as you cool down. And because it's under tension, it's the worst case because we all know that a failure mode for tension is cracking. And so you can develop cracks in this film as it's cooled down. And so the classic problem here is that the strain that builds up along those directions is related to the delta alpha delta t, right? So it's the difference between these two. Remember, because they're linked at the growth temperature, and as you cool, it's the difference between those two as you cool that induces the strain and the stress. And so that's just a little example of that. To give you an idea of all these materials, like I said, because if you think about bonding, they're all basically, not that different from a bonding perspective. And so everything's in the 10 to minus 6 range. Of course, you can change the front part, to be tens of 10 to minus 6 instead of just single digit 10 to minus 6. So there are substantial differences, but it's not going to be orders of magnitude difference. And there's some like rule of thumbs, right? Like if you look, bonding is controlled by the periodic table, which smoothly moves as we do different orbitals across the whole thing. So like you suspect, there are smooth changes in thermal expansion that you might expect. And for example, if you were to look at a melting point, which is related to of course bonding, right? The stronger the bond, the higher the melting point. And then if we were to look at alpha in 10 to the minus 6, again, you would see that over here we have sulfur and lithium, and this kind of comes way down here. And down here we'd have tungsten. So this is like 3,700. And then these guys here are around 400. And you see an interesting relationship that alpha is empirical relationship. And as I said, this makes sense because it smoothly changes across you have a smooth change across the periodic table, changing the bonding strength, changing the orbitals, and so you'd expect something to this effect. For compounds, those are materials made up of elements. But compounds, ionic compounds, remember we have to keep on looking at different ones, but if we look at ionic compounds, you see a very similar curve, and in that case, alpha equals 0.038 over Tm. And I should put that this is right. So some general trends following the bonding principles that we've discussed, and hopefully this is creating a nice unified picture for you, at least in terms of the bonding that we've done and the periodic table and thermal expansion.